Hello, students. Paul Austin here in Computer Science Foundations. We're going to look at vectors and bitmaps a bit with Python today, as it relates particularly to some of the programs we've been dealing with already. Here's some of the definitions we'll touch on in the next few units. First, the vectors and bitmaps, and then nested loops and how they're useful with working with bitmap type data. And this gives you a little glimpse into how GPUs and why they exist and how they help your game playing and other kinds of rendering. For Python, we'll use X and range. We'll also touch on Boolean expressions. We'll start to see how tuples, a set of numbers paired, how they are useful. And for turtle graphics, we've seen some of these before, but how to make high performance using the turtle graphics. Well, high performance is a bit of a joke there, but how to make it really fast. Turtle graphics continues to be a nice package to start with. Ultimately, if you're doing games, you'd be working with another tool. Anyhow, let's proceed. Let's look at where we were with our Python examples. This was the Koch curve. You're drawing a snowflake, and if you remember our patterning on here, we see the drawing. Now notice when it's drawing, you can actually see it's obviously much slower than it would be if we let it run full speed. But you see how it's drawn line by line. That's an example of what you consider vector drawing. If we look at the code here, I'll go ahead and click that out here. All the drawing basically happens in this program. There's one line. This is where the forward statement, where you're actually telling it to move forward. There are other parts related to the drawing. They don't actually paint pictures on the screen, but when we tell the turtle to turn right, and to turn left, and turn right, and there's one up there. So there's the turns, which just change the direction. The only thing that actually draws, though, is the forward statement. And if we look at how that might render itself, this is a little bit what's happening on, if you imagine a piece of graph paper. That's one of the reasons Turtle Graphics is nice. It's kind of designed around the idea of a piece of graph paper, just like you would use it in math class. So what's happening is we start at a given point, we move forward, and then we're going to turn left. Oh, if I get that click on here, we're going to turn left, move up, and we're going to turn right 120 degrees and move forward again, turn left, and then move forward. So that's an example of vector drawing. Everything is basically described as how you would move a pen, just like you're in art class. In fact, artists typically use vector-based drawing. You might have heard of Adobe Illustrator, Affinity Draw. There's a lot of different drawing packages, which are primarily done by the vectors. One nice piece about that, we can't dive into too much here, is that vectors, no matter how far you scale in, the endpoints are known mathematically. And because of that, the lines can be sharp and crisp, know how far deep you go in. Fonts, the way you see the letters are defined through vectors now. And so if you go on a printer or a high-resolution device, the letters still look crisp. It's a big step many years ago when everything was bitmaps, not just Mario. All right, so, well, I guess to touch on that one bit on here, that's not what I'm looking for. There we go. When the drawing actually happens on the screen, ultimately pixels are set. Fortunately, with a package like Turtle, you don't have to think of the pixels, but the pixels are actually the picture elements. That's what pixels means. The picture elements are set, and if you had a really coarse display or you're looking at something from the 1970s, you'd be able to see these pixels set. Right here I have it zoomed in, but honestly, if I come back to this package here, and if I zoom in, I'm not sure that's going to capture it on the capture tool, but you'll see the actual stair steps that are there. All right, let's go back to our Python code here. Let's see, there we go. All right, but what if instead of calculating endpoints, we actually wanted to set each individual pixel? What if we wanted to be able to control the picture pixel by pixel? After all, our eyes see things fundamentally in elements. They're not rectangular, but are the rods and cones in the back of our eyes and see individual dots of light. And levels above that begin to make the image we have. So let's look at how we would actually draw a picture pixel by pixel. Okay, our Python program, we'll start off with our standard import turtle. There we go. We might need math, but we'll skip it for right now. Turtle.tracer. We always got to do this if we want things to go as fast as Turtle can go. Turtle. Oh, what is it? Oh, I can see here. Make an actual individual object. That equals there. T dot pin up. You don't need to draw that. Remember to do the function call. T dot speed. We'll go -1. And let's do the start. We're ready to draw. Normally we're thinking of the turtle drawing lines, but we're going to do a different approach. We're going to use a function called t dot dot, or turtle. So if I did t dot, I can specify that it's going to draw a given dot of a radius and then a color. Start off with here, blue. That'll be French. There we go. All right, so the simplest one, if I ran that, we got to give it a name. We'll call it dots. All right, there, 1 dot, not a whole lot. So let's now draw a bunch of dots. They'll be the picture elements. Tell you what we're going to do. We're going to end up making a grid. Let's pick a size. We don't want to hard code our code too much, so we'll give it 200. And then we're going to say for X in range minus size, and we're gonna make it steps. If I did it individual pixel by individual pixel, it would be pretty slow with the package with Turtle. So although I like the fact about the speed, you actually get to see the picture draw incrementally. When it all happens like that, you don't actually get to appreciate how the picture is built up. So there's some upsides to that. All right. So now run this. Oh, wait. Oh, look, I'm only drawing. I haven't moved anywhere. So t dot go to. This is why I went ahead and did the pin up, so I don't have to see that. If we go to the X location, and then we'll go ahead and keep it on 0 here. There we go. We got a whole line of dots. So that's not a grid. That's just one line. What if we want to do this, from one line, we wanted to do 2 dimensions? Well, this is where nested loops come in. So we'll just go ahead and add for X. We'll go ahead and do an inner loop now. And if we do this, now we're going to go take X from the left to right, and then we're going to take the Y, and we're going to go to the Y from the bottom to the top. So let's try run that. All right. Where is it all? Oh, wait, no, there it is. You know what? We still did it all at 0. So we go this. Now, where is that picture? Oh, wait, there it is. Okay. So here's another tip about Turtle graphics, and in here is when you do the tracer of 0, you're not going to see it until it buffers a lot of the drawing bit by bit. So what we have to do is say t.update. Things like the update, even for advanced graphics packages, you'll see things like OpenGL or rendering packages. That idea of saying do all the work until you can as fast as possible, but then having a spot where you say, okay, I want this picture to be pushed out to the user. It's a common pattern you'll see in a lot of tools, not just graphics. So here's a tip here. If I do this, we can start running this, and let's see. Oh wait, look at that. And that's because this is not on new turtle. There we go. Right. Now we're seeing it, and it's going, but it's going pretty slow. So we're going to do compromise. Instead of saying we want to update after every single drawing, what we'll do is we'll turn around and say, I want it to do an entire Y range. Once that's done, we'll just draw that in one shot. See how that looks here. Okay. It's a little faster. It's a little more reasonable for our graphics right here. So now we have turned around and we've painted a square, filled square, in a very slow way. But this is in fact what's happening behind the scenes when like a rectangle is being painted. It's just being done at a much lower level, closer to the hardware. And every one of these dots is actually a little circle. I'm going to zoom in on here. I don't know if that would be done in the screen capture. Little circle in there. Now, what can we do at this point? Let's see, is there anything else? Well, I guess we only want to make each unit on this video not too complex. What we're going to do on one piece on here to set up a T for the next one is, instead of passing the color as a name, we can actually begin to realize that pixels are made of colors, and the colors are defined in red, blue, and green. For different printing processes, sometimes you'll see other things. You'll see cyan, magenta, yellow, but red, blue, and green is the most common ones. So I can here, I'm going to pass in red, we'll say 0, blue, that was what we were doing here, 1, and green was 0. I'm going to pass in a numerical way to describe a color for that circle. If you run here, now I'm getting, oh, well, it's not red, blue, green, it's red, green, blue. Showing some old Windows flashbacks there. So RGB. So I could add blue to it, and we'll see this. This case, in this mathematical model that's being used here, 0 means none of the color, and 1, or 1.0, means as much of that color as you can put. So if I do, in this case, it's red, and I'll put the 0.0 just so you sort of see that. They are floating point numbers as far as the color goes. So this is going to be no red, and a lot of blue, and a lot of green. We'll take that, run this color on here, and that's what gives us the color cyan. If I did white, which was 1.0, we wouldn't even see it. So RGB, take it 0. Let's see what we get on here. I'm hoping for a bit of a purplish color, and there we got it. All right, that's it for this lesson. We'll pick up with the next one. All right, take care.